All right, so we're going to pick back up in section 7.2 where we left off. We're going to look at this example here. I have the identities that we need on screen in case we don't have them written down. I'm not going to linger too long on those, so if you need them, you can pause the video and write them down. The problem we have here is rewrite f of x equals 4 times sine of 3x plus pi over 3 as a sum of sine and cosine. Let's see, I have a sine function. Inside of this sine function, I have a sum. So I have to use a sum of angles identity for the sine function. So I'm going to use this one right here. So this is going to be 4 times, and in parentheses I'm going to have my identity. It's going to be sine of 3x times cosine of pi over 3. Plus cosine of 3x times sine of pi over 3. Now, whenever I evaluate these, this becomes 4 times cosine of pi over 3. This is 1/2. I'm going to write this as 1/2 times sine of 3x. Plus sine of pi over 3. This is square root of 3 over 2 times cosine of 3x. And whenever I distribute this 4, this becomes 2 sine of 3x plus 2 root 3 cosine of 3x. So notice that the result here is a stretch of the sine function added to a different stretch of the cosine function. But both of these functions have the same horizontal compression. They both have the same horizontal compression by a factor of 1/3. And this results in these two functions having the same period. So we might ask whether this process can be reversed. Can a combination of sine and cosine functions be rewritten as a single sinusoidal function? And in fact, they can. To rewrite m sine of bx plus n cosine of bx as a sine of bx plus c, first to find you can find this a by using a squared equals m squared plus n squared. Cosine of c equals m over a, and sine of c equals n over a. This says you can use either of the last two equations to solve for possible values of c. But since there will usually be two possible solutions, we're going to actually have to look at both of them anyway to determine which quadrant c is in and to determine which solution for c satisfies both equations. So I'm going to carry this with us to this example. Oh, there we go. I had accidentally pasted over the example there. We want to rewrite 4 square root of 3 sine of 2x minus 4 cosine of 2x as a single sinusoidal function. So I have some m times sine of bx plus n times cosine of bx. So this is important. I have to make sure that the horizontal stretch or compression of these functions is the same, so that they'll have the same period. And in fact, that's true, right? I have a 2 inside of both of these functions. It's important to notice that in this equation, I have a b inside of both of these. And in fact, that's the same b that I'll have inside of my final function. So this means I already know that b is going to be 2. A squared is m squared plus n squared. So a squared, this is 4 root 3 squared plus negative 4 squared. 4 root 3, this is 16 times 3, which is, 4 root 3 squared is 16 times 3, which is 48. Negative 4 squared is 16. So a squared is 64. If a squared is 64, this means that a is 8. So now, to solve for c, I need to use cosine of c as m over a, and sine of c is n over a. So cosine of c is going to be 4 root 3 over 8. This is square root of 3 over 2. So if cosine of c is square root of 3 over 2, there's a cosine value of square root of 3 over 2 at the angles pi over 6 or 11 pi over 6. Now I have to determine which of these is going to be my solution. And to do that, I have to find sine of c. Sine of c is n over a. So sine of c, this is going to be negative 4 over 8. N was negative 4, and a was 8. And this is negative 1/2. Without even having to look at where the sine function has a value of negative 1/2, I know that this has to be on the bottom half of the unit circle. This has to be quadrant 3 or 4, because those are the quadrants where sine is negative. This angle is in quadrant 1. This angle is in quadrant 4. It's going to have to be that one. If you did find the two places where sine of c was equal to negative 1/2, of course, this would be c equals, what would this be? 7 pi over 6 or 11 pi over 6. And notice that we have one that matches here, right? So I know what my c is, I know what my a is, and I know what my b is. My b was given to me. So c is 11 pi over 6, b is 2, a is 8. And I can write this as a times bx plus c. So 8 times, or not a times bx plus c, but a times sine of bx plus c. So a times sine of 2x plus 11 pi over 6. And this is our answer. For this next problem, this is saying solve 3 sine of 2x plus 4 cosine of 2x equals 1 to find two positive solutions. The first thing I want to do here is I want to rewrite everything in terms of a single sinusoidal function on the left-hand side, because otherwise this is very difficult to solve. So let's first find a. This is using the formula from the last page. Let's see, is it still in my copy and paste? Yeah. So a squared is going to be m squared plus n squared. So this is 3 squared plus 4 squared. So a squared is 25. So a is 5. Cosine of c is, this is m over a. So this is 3/5. Here, I have to use the arc cosine function, or the inverse cosine function, to solve, because there is no cosine value of 3/5 on my unit circle. So c is arc cosine of 3/5. And if I find arc cosine of 3/5, this is about 0.927. This is going to be in quadrant 1. My other answer is going to be in quadrant 4, because that's where else cosine is positive. So c could be 2 pi minus arc cosine of 3/5. And this would get me about 5.356. And this is going to be my quadrant 4 angle. Now I have to determine which of these angles C is, right? And I can determine that by now looking at sine of C. Sine of C is 4/5. Well, sine of C is positive here, right? Because this is positive. This means that C is in Q1 or Q2, because sine is positive in quadrant 1 or quadrant 2. So C is 0.927. So I can write my equation now. I said that A was 5. Right. This is 5 times sine of, I didn't state what B was, but B is this 2 x plus, I said that C was this 0.927. And I want to solve for where this is equal to 1. Well, I can isolate my sine function now by dividing both sides by 5. I can now take the arc cosine, or the inverse cosine, of both sides. Although, let's see here. Would it be better for us to use a substitution at first here? It might be safer for us to use a substitution at first here. So let's be careful and use a substitution. Let's let u equal the stuff on the inside of the function. So this becomes sine of u equals 1/5. Sometimes we can make mistakes if we don't make a substitution like this. We can subtract or divide stuff too early, basically. So solving for u, this is arc sine of 1/5. Arc sine of 1/5 is about 0.201. This is in quadrant 1. The sine function's also positive in quadrant 2. Because this is in quadrant 1, this is actually my reference angle. Right. Angles in quadrant 1 are reference angles. This is my reference angle. So if I want to find an angle in quadrant 2 with an equivalent sine value, then I can do so by taking pi and subtracting this reference angle. I just have to rotate clockwise by this amount from pi to get an angle in quadrant 2 that has the same sine value. So this is going to be pi minus arcsine of 1/5, which is about 2.940. Now, normally we would leave it at this, but this is asking us for two positive solutions. And once we undo the substitution, I think that once we subtract this 0.927 from both sides, we're going to get a negative answer for this one. So we should go ahead and try to find a third possible solution here, because I want to make sure I have two positive solutions. So to do that, I can just find an angle that's coterminal to this 0.201. This would be 0.201 plus 2 pi, which would be 6.485. This is coterminal to 0.201. Just so I can make sure I'm going to have two positive solutions. So now I have u equals these things. I want to undo my substitution. Remember that u was equal to 2x plus 0.927. So now I have 2x plus 0.927 equals 0.201. I also have 2x plus 0.927 equals 2.940. We'll go ahead and solve these two. Subtracting 0.927 from both sides, we get negative 0.726. Dividing both sides by 2, we get x is equal to negative 0.363. So this is not one of our solutions. We wanted two positive solutions according to the problem statement. And this next one, subtracting 0.927 from both sides, leaves us with 2x equals 2.013. And dividing both sides by 2 gets us that x is about 1.007. I guess you could say 6.5. We'll round to 7. This is a positive solution. This is good. I need one more positive solution. So the last thing that we had to do was we had u equals 6.485. So 2x plus 0.927 equals 6.485. Subtracting 0.927 from both sides, we get 5.558. And dividing both sides by 2, we get x equals 2.779. So we eliminate that negative solution, and we just keep these two positive solutions as we were asked for in our problem statement.